There you go.
All righty. Welcome to Cosmology seminar number 1. We've special week here at Laterno. I don't think we've ever had a cosmology week at Laterno University since I've been here, and maybe since Dr. DeBoer has been here. So this is something new, something special. We've got two special speakers who are cosmologists working in the field. And I'm not going to waste any time because he's got a lot to share with you. But this is Dr. Mustapha, Ishak, who is professor of physics and astrophysics at UT Dallas, where he's been for, let's see, how long have you been there?
Almost like 14 years.
14 years. And this guy, I've got so many things I could say about him that I don't have time, but he's won the Outstanding Professor of the Year award from the School of Natural Sciences and Mathematics, not once, but twice. He must be good. So, he's an expert in dark energy and the accelerating expansion of the universe. He was born in Algeria, but he came to Canada to do his education, both computer science and physics, both at the University of Quebec and then the University of Montreal. And then he got his PhD in cosmology and general relativity at the Queen's University at Kingston, Canada. And this guy has so many publications, I can't list them. So let's just give this guy a warm welcome.
Thank you for the introduction, and I'm very happy to be here, and it's really nice to see all the students here. So what I will do today is, from this talk, I will have an objective. So first of all, I will give you some context about cosmic acceleration, and then after that, I will talk a little bit about the evidence for it when it was discovered and for the last 2 decades. And then after that, I am hoping that when you leave this talk, you will remember what are the 4 possible causes of cosmic acceleration. So there are 4 possible causes of cosmic acceleration, so we will go over them one by one. So first of all, I should name some of my graduate students. I worked with them over the years on the problem of cosmic acceleration. And so some of them are actually now, Jacob is a professor at University of Dallas, and Troxel, he got a job at Duke, and these guys, and Austin Peel is somewhere in Paris doing research. So they share some of the work that I did in the last decade. So now, I will do something unusual, so I will start by a summary of my talk, okay? So, what can be the cause of cosmic acceleration? So it could be a repulsive dark energy component. It could be a general relativity cosmological constant of nature, so it's just a constant of nature. And then it could be also a modification to general relativity at cosmological scales, so that we call modified gravity. And then it could be also another thing, it could be that this acceleration is only an apparent effect because we live in a more complicated cosmological model. It's still general relativity, but we will see that that one is not really a viable solution. It could be, finally, it could be something that is completely unexpected. Something just like 100 years ago, when Einstein came up with general relativity and special relativity, there were big questions. Yes?
What is FLRW?
Friedman, Lemaitre, Robertson, Walker model. It's the model of cosmology. And that actually supports the fact that I took this slide from the end and I put it at the top. Okay, good. So, two decades ago, there was this discovery of cosmic acceleration. And this is the team that got the Nobel Prize in 2011 for it. So I will tell you a nice anecdote, so now that you see them. So Brian Schmidt and Adam Rees, they were working in Northeast, and Saul Perlmutter was working at Berkeley on cosmic acceleration. Both of them discovered this at the same time. So, and again, I think this is a course of some of you are taking the course in cosmology. So what is cosmology? Cosmology is interested in the science of the universe as a whole. So cosmologists get interested in the small details of matter and what is happening, as long as it gives us an understanding of the universe at very large scales. So cosmology applies the physics to the universe as a whole. And some of you have seen this, but again, you go from planets to galaxies, from galaxies to clusters of galaxies, from clusters to superclusters of galaxies, and then you have this kind of cosmic foam. All the filaments here are galaxies and clusters of galaxies. And this one is a picture of the CMB, or the cosmic microwave background radiation. I will get back to it a little bit later. So now let's get some context, okay? Let's get us a little bit into the context of cosmology. So 100 years ago, when general relativity of Einstein came, there were two pieces of information. There was the first one. The first one is by these two guys here. So Alexander Friedman and Lemaitre. So these two guys had these ideas of a primary universe that was dense and hot, and then that expanded in what we see today. So it's an idea about physics, it's an idea about astrophysics or cosmology, how the universe was in the past and how it is today. At the same time, these two guys, Robertson and Walker, they were working on a mathematical model of the geometry of the universe, based on homogeneity and isotropy. You see, when you look at this picture here, when you look here, you see, if you look larger and larger, the universe becomes what we call isotropic. That means if you look in some direction, it looks all the same as in this direction, we call that global isotropy. And also homogeneous, as we know what homogeneous is, so it's just a homogeneous distribution of matter. So now, from what general relativity did, and this was a fantastic coincidence, that general relativity connected these two pieces of information. It connected the ideas of Alexander Friedman and Lemaitre with the mathematical model of these two guys. So what general relativity did, it took the space-time, or it took the model of these guys, and it put it into the general relativity equations. I promise you I'm not going to show a lot of math, just enough so we understand, and I will explain whatever I will present. So the only idea here that I want to get from this is that the idea of general relativity, what it does, what it did, and what it's still doing. So the universe is full of matter. It's full of galaxies. It's full of clusters of galaxies. And it's full of energy. So all this, we call it the matter content in the universe. All this matter content and energy content is actually related to the geometry of space-time. It's related to the motion of space-time. And exactly when we talk about Einstein field equations, we will all remember now that Einstein equations, they connect the geometry of space-time, the geometry of space, to its matter content. That's what general relativity did. And you can write them, you can write either these equations like this, or you can write this equation with this additional term here, a lambda. This lambda is a cosmological constant. We'll talk a little bit more about it later. So if you take the Friedman metric and you put it into Einstein field equations, what it gives you these two equations. These two equations are the equations, in fact, that governs the expansion of the universe. The first one right here is an expansion equation. When you look at it, you see a dot here. A dot, so A dot over A. So what it means, a first time derivative, a derivative of x with respect to time, or a first time derivative, is something like a velocity, okay? So it's something like a velocity, and that's exactly what it is. This first equation is an equation of the expansion of the universe. And the second one, some of you have already noticed the double dot here, and that is 2 times the derivative with respect to time. And that is an acceleration. So this one is an equation for the expansion of the universe, and this one is an equation for the acceleration of the universe. In fact, these equations surprised Einstein a little bit. They surprised him because at the time when he got these equations, he got them like this, and then he didn't like them because they did not give a static universe. They gave a universe that is either expanding or contracting, but not static. And at the time, the establishment wanted the static universe closed and finite. So what he did actually, he introduced this cosmological constant, and it's not a mistake that he introduced it. It's a mistake that he gave it a specific value to make the universe static and finite, okay? So when he met with Edwin Hubble, and Hubble showed him that Friedman was right, the universe is rather expanding, he said it's the biggest blunder of his life. That's what Einstein said. But then later on, 20 years ago, the cosmological constant is back. So maybe Einstein is right even in his mistakes. Now you look at these 2 equations. In fact, these are the basis of the expansion of the universe. So again, I wanted to give a picture to some of you that this is the idea of general relativity. So massive objects, they curve space-time. And in fact, if you take a piece of paper and you just fold it like this, if you put a pencil on the side, it falls towards the curvature of the universe. So the universe actually, the fact that it's expanding, it's just that objects are falling. Objects are following gravity, and that gives an expansion. However, the acceleration is a different thing. General relativity predicts the expansion of the universe. It's exactly the law of gravity. But general relativity does not naturally predict an acceleration for the expansion. Well, this is another wonderful thing about cosmology today. Okay? The wonderful thing about cosmology today is that there are what we call cosmological probes. Okay? Like cosmological probes or cosmological data or techniques to measure the universe, to observe in the universe. What is good about it is, for example, I will name some of them. This is called the microwave background radiation. And I will talk in a minute about it. And this is called, this supernovae and distances to supernovae. This is called gravitational lensing. And this is called, for example, galaxy counts or surveys, photometric or spectroscopic galaxy surveys. What is good today about cosmology, if you have 7 or 8 probes, you can wake up one morning and say, you know what, I don't like these 2 probes, I don't trust them enough, okay? You have 5 more that you can work with. It's called complementarity in cosmology. Well, here is the story of the CMB. So, one of the pillars that confirms the theory of the Big Bang that we talked about of Friedman, Lemaitre, Robertson, and Walker, one of the pillars is the discovery of this radiation. So from the time when there was the Big Bang, the universe was dense and hot plasma. So the photons were at about 3,000 Kelvin. And then the universe was dense. Then it started expanding in all directions. So Gamov, who is here, said if such a state of the universe existed in the past, it has to be that some relic radiation has been left for today to observe. not only he said that, but he also did some calculations, not all of them correct, but he predicted that such a radiation should be about 5 kelvins. The temperature should be 5 kelvins. A little bit later, some other people were doing, some other scientists, so Penzias and Wilson, they were doing some experiment for Bell Labs. They were trying to, they had an antenna, but they had some noise in the antenna. When they directed this antenna in many directions, each time they had a noise. They had a signal that is like noise. It turned them crazy. They wanted to get rid of it. They couldn't. And then they called these guys here. They called them these were at Princeton. I had the pleasure to meet and work with Jim Peeble, who was still active when I was at Princeton, so I worked with him. And at that time in the 60s, what he did, these guys, they said, well, you just detected something. You just detected something that we are building an antenna specially to kind of measure it, okay? So so these guys, Penzias and Wilson, they get the Nobel Prize for the discovery of the CMB. In fact, you don't need to have a very sophisticated antenna. Some of you here in the room, like me, who remember this TV where we can see the snow on TV, okay? Some of that snow on TV is actually the CMB, okay? And here in this room, look, every centimeter cube, okay? Every centimeter cube, there are about 400 photons of the CMB passing through that, okay? So it's impressive. When this was discovered, there was no question about the Big Bang Theory, that this is a pillar of the Big Bang Theory. Well, so we learned a lot about our universe based on the Big Bang model. We learned the age of the universe, about 14 billion years, 13.8 billion years. We learned about structure formation. We learned about the CMB. We learned, and we also now have at least 7 or 8 cosmological probes. You use the ones you like. You don't use the one you don't like. But then we have 2 problems, though, two puzzles. The first puzzle is called the dark matter problem. Dark matter, and that's not what I'm going to talk about today. Dark matter is something like it's something that is gravitationally attractive. So if I have a pointer of dark matter, I will throw it to the ceiling, it will go up, stop, and it's come back because it's attractive. That dark matter, there is 90% of it, of the matter. And again, the nice thing about cosmology today, there are about 5 different ways to measure or to probe dark matter. And that's the nice thing, it's called complementarity between probes. But we will skip that maybe for another time. Now we will talk about dark energy. This is even more difficult. As if it was enough to have dark matter to deal with, now we have to deal yet with another problem. So dark energy is related to cosmic acceleration. So it's like repulsive gravity. So why is it? There are 2 things about it. 1, it's unexpected behavior. And 2 it's unexpected behavior, and 2, it's a dominant component in the universe. So before I go then to the proof of it, so yes, so it's like here what I meant. If I take this is what it means, dark energy or cosmic acceleration. It means if I throw this pointer to the ceiling, it will go up. When it's about to reach the ceiling, it's not going to slow down and stop. It will fire up. It will go again like repulsive gravity. So that's what we're not used to it. So the question is, I am here today to try to explain to you what are the causes, what could cause such a repulsive gravity, such an acceleration in the universe. That's the goal. But I know I gave a talk like this, like for 10 years ago, I used to kind of spend a lot of time on the proof that there is cosmic acceleration. But then it became boring after 10 years. So I changed, I just kept a few slides. This slide, you see this is a supernova here, and it's as bright as a galaxy. It's as bright as 10 to the 9 suns, stars. So it's really very bright. Since they are bright, we can see them very far in the universe. If we can see them very far in the universe, we have ways to measure distances to them. And what we found, so here is a kind of a summary. This summary, I can tell you the same thing is like when you drive at night. You know an approximate, your eyes, they know about an approximate light of the car lights. So by seeing the intensity of the light, the observed flux with your eyes of the light, you know about the intrinsic luminosity of the light, then you can determine approximately the distance. That's exactly the same thing for supernovae. We know that there are bulbs that lights at minus 19.5 magnitude. That's the intrinsic luminosity. We measure their flux or their apparent luminosity, and that gives us an information about their distance. And guess what? This is now the nice story that happened. And then we have a theory how to measure these distances here. And then we compare the distance with observations. Before we go to these plots here, now is a good time to go back to our friends at the beginning, the 3 guys who made the discovery of the cosmic acceleration. So they went to try to prove actually cosmic deceleration. That's what they meant. Their projects, both of them 2 teams, they wanted to prove cosmic deceleration. And let me tell you that sometimes it's a very nice thing in science that you try to prove something, and you just prove the opposite. It happened to me. It happened to me. I will show you in the last slides, I will show you. It happened to me, but actually it proved something good, so something important. So the 2 of them, so Schmidt and Adam Rees, they were trying to look at the supernovae and see that as you go very far, they are slowing down the distances. This is like when you look at a car moving away from you. If you look at it, and then after each time you see it not as far as you think it would be. If it's moving at a constant speed from you, away from you, you can predict where it will be. It's moving from you at a constant speed. But then if it's slowing down, you expect to see it a little bit closer, a little bit closer, and a little bit closer, if it's slowing down. If it's going faster from you, you will see it, each time you'll find it farther. So Adam Rees and Schmidt and Sol Perlmutter at Berkeley, they were looking at the supernovae and trying to measure the distances to them, expecting to find them closer and closer. So they measured deceleration. But after 1.5 years, no results were coming from these guys. So they are working on it in silence, nothing is happening. So until one of them picked up the phone and called me out once. Hi guys, how is it going? And are you seeing something weird? Then the other one says, maybe, how about you? Okay? And then they communicated, they were both observing cosmic acceleration instead of deceleration. And here we go, this is only one example. So already in a little bit before 1998, so already a little bit before they were already C96. So Mario Hamway, in 1996, they already saw some glimpse of cosmic acceleration. And then that was pursued by the other guys as well to look for, these are the famous plots that found discovery of cosmic acceleration. You see Adam Rees et al. And Sol Perlmutter et al. These are the 2 teams. So they found out that the data goes a little bit up here, and then on a differential here plot, you see that the data here, look at the data here. This data here, this supports omega lambda and acceleration, while this curve doesn't. And then same here, the curve up support cosmic acceleration, while the others don't. And then if you look here, clearly the data favor this line up. But this was a long time ago, 2003. Now we continue, so for the last many years, the support continues and continues. This is the plot that I like. I will get, and there are many of them, years after years. I used to collect these, but now I don't. So look at the value here at omega lambda. And look at the value here, 0.679 plus or minus 0.013. Look at the precision again, 0.699, 0.012. There is no way in cosmology today that omega lambda is 0. And this omega lambda is the omega, is a quantity that shows the cosmological constant is there. For the last 20 years, no exception, about 20 or 30 experiments, they all show something. This is just from last summer, right? This is in 2018. And then all of them, they agree with one single point. Look at the omega lambda in this plot. Is about 0.7 here. So this 70% shows the dynamics of acceleration. Now, why is it so important? You can tell me, why is it so important that the cosmological constant or the cosmic acceleration is an important thing? Not only it tells us this weird thing of the repulsive gravity. I find it weird, okay? It's repulsive gravity. And second, in addition to that, when you do mathematical physics, or you try to understand the theory, the unified theory of the universe, the cosmological constant also goes, also goes in the equation, in the Lagrangian equations. It goes in some fundamental equations. It makes it that the cosmological constant also touches important theories of the universe, like string theory, or GUT, the unified theory, or grand unified theory. So there is a fundamental reason why the cosmological constant is also a challenge to physics. Well, so for these two reasons, now we start with our decount. We start. So out of 4 reasons for cosmic acceleration, we start with the first one. The one that you hear about, the name dark energy, okay? What is something that physicists are not very good at? Tell me. Did you notice something? I noticed something a long time ago, and I think you all know about it. In fact, I was wondering if it's just physicists because I do physics, or it's just all scientists in general. We are not good at giving names to things. That's what we are not good at. Do you know that the word Big Bang is actually was given to kind of mock the idea? So it's Fred Hoyle when he said he wants to give a talk, and he said he did not believe in the Big Bang, but when the CMB came out, he questioned a little bit, but he still didn't want to believe in it in the 60s. So he mocked, actually, he said, what is this theory of the Big Bang? And then it stayed with it. So there's a lot of things in physics that have a name, even black holes as well. So all these, so the same thing, dark energy. So dark energy is only a buzzword but really the real question is cosmic acceleration. What is the reason of cosmic acceleration? Only one explanation can be dark energy, if you want. And actually, this word was coined by some particle physicists because they wanted to get money from the Department of Energy, okay? When they write their proposals. So when you put dark energy, you can get some money from DOE, okay? Mea culpa too a little bit. So I got some money, but a long time after that. So one explanation is that in the universe, there could be another form of energy. And that form of energy, if you put it within the Einstein field equations, it can generate repulsive gravity. It can generate repulsive gravity. It's called, so now you ask me the question, you say, is it possible that such a different form of energy exists? Dark energy. The answer is possibly yes. And the first candidate for such a new form of energy, that is called dark energy, is called actually vacuum energy. Vacuum energy. So in quantum field theory, the empty space, there is no such a thing of empty space or vacuum. It doesn't exist. It's the zero level energy of quantum fluctuations. And that zero level or zero state of quantum field has some energy associated with it. It was predicted in the 60s by Zeldovich, Jakob Zeldovich and other people, that there is this vacuum energy, and it coincides that it has exactly the properties that cosmological constant can have. And in 1948, I believe, or around that, in fact, there is a German physicist called Casimir. He actually predicted that if such a vacuum energy exists, it will actually make two plates in vacuum attract each other. Now I know what you are thinking. You say, if it is repulsive, shouldn't the plates be actually pushed apart? No, because when you have the two plates, the space in between the two plates is small compared to the vacuum outside the plates. So it is the vacuum outside is pushing the plates to get closer together. This Casimir effect has been measured in the last 30 or 40 years to a 1% precision, Casimir effect. It tells us that the vacuum is not completely vacuum. And here is the idea, this is a cartoon idea, to tell us that here what dark energy, this is like matter and dark matter here. It curves the space-time in a positive way. Tell me if you put here, I want to get you into this plot here. So if you put a marble here at this end and you put a marble at this end, right? And you let them go. What are they going to happen to the two marbles? They fall to the center. They fall toward each other. Okay? And you have here a massive object, for example, here. So they will fall towards the center of the massive object. So that's kind of the idea of general relativity of Einstein, the curvature of space-time, so objects are falling towards. It's a little bit more complicated than that, but it's just a cartoon way to understand it. But here is the idea of a negatively curved space-time. If you put two marbles here at the top, what's going to happen to those marbles? They're going to go away, apart one from the other. So that's the idea of the negative curvature of space-time. Not the space of space-time, but curvature of space-time. Well, I promise that I'm not going to show you equations anymore, but sorry, Shaggy, but I will just show you this one. So you understand, and I think some of you have been doing some of this already. So we talked about, this is the acceleration, right? A double dot. If A double dot is positive or A double dot is negative, so it's either an acceleration or a deceleration. So general relativity of Einstein, if you put in this universe a form of energy like vacuum energy, and actually you give it what we call a relationship between P and rho. This is the pressure and this is the energy density. If this W is called the equation of state. if you came across this word, the equation of state of dark energy, raise your hand if you are familiar with it, if anyone heard about it. Okay, thank you. So the equation of state of dark energy, W, so this is a very easy arithmetics here. So if you look, this is negative, and this one, if W is smaller than 1/3, in negatively, more negative than minus 1/3, so this guy will be negative, and this is negative with the minus sign here, so we obtain a positive A double dot, so it's an acceleration. So if you find in this universe, if vacuum energy is there, if dark energy is there, if it has a relationship between the pressure and the density such that this W is smaller than minus 1/3, then it will generate cosmic acceleration. Well, this is just to tell you that behind this discussion of vacuum energy, there are some very neat calculations, like for quantum field theory. There's some very neat calculations that supports that, okay? So in this case, you see the W is equal to -1, which is certainly smaller than minus 1/3. Well, let's go back now to the second. So tell me now, all of you, so the first, so you can remember them after this talk. So the first possibility is dark energy. And if you are asked, what is this dark energy? You can tell them that it is shown in physics that vacuum is not really vacuum. Vacuum has zero-state quantum field theory energy in it. And that can act as vacuum energy. And that can actually make the acceleration of the universe. That's possibility 1. Let's go to possibility 2. This one is, so Newton is saying, okay, he has a constant, Newton constant, so everyone can have a constant. Why I'm saying this second possibility? It is quite possible that the laws of gravity, okay, the laws of gravity have a constant that is G here. G is a Newton constant. In the same way that gravity has a constant that is Newton constant, it could be that the universe has another constant which is called the cosmological constant of general relativity. It is enough to have a cosmological constant, just a geometrical constant of nature, and that will produce cosmic acceleration. And we don't even have to justify the value of such a constant. What do we do with constants in nature? Anyone? What we do? We set experiments and we measure them. So the cosmological constants, this geometrical constant, can make the universe accelerate. However, this solution makes my friends in general relativity very happy, okay? But it doesn't make the rest of the other physicists happy, okay? Because of quantum field theory is tested to 10 to the minus 11 precision. So this solution of a geometrical constant is only a solution for relativists who don't want to look at quantum field theory and wants to ignore the rest of physics. They say, I'm happy with a GR cosmological constant. I don't mind about the other thing. So then in that case, this is not as satisfactory. But I can tell you what, the things that sometimes we neglect or think they are the less possible. I actually walked away from this solution for 10 years. And in the last year or so, I started going back to this solution. Okay, why? Because if we can find a mechanism by which to explain how vacuum energy does not gravitate, does not contribute to gravity, then this solution will be by far the best one. But then the task, the very difficult task, is to prove that vacuum energy, even if it exists, it doesn't gravitate the same way as the other matter. Well, so this is the second solution. So let's summarize. One is dark energy. 2, a constant of nature. So 1, dark energy. 2, a constant of nature. And now we continue with the third one. Yes, Albert, maybe you did a mistake. Okay? So it is possible that in the same way that Newton gravity ceased to be valid close to a black hole, or you all know that if our GPS, okay, if our GPS doesn't have into it, if you put a Newtonian gravity in the GPS, okay, and you don't put Einstein gravity in the GPS, anyone knows what's going to happen? Anyone?
Position's gonna be off because of the.
Yes, the position will be off. Your GPS has GR programmed, thank you. Your GPS has general relativity programmed into it. And if that is not there, but I know what you are thinking, maybe some of you are thinking. I maybe thought that the first time I heard. Oh, maybe they think it will be off by a meter or two, so it's not that important. Actually, that's not true. Because if you don't put general relativity and special relativity in our GPS, in one day, your GPS will be off by 17 kilometers. One day, 17 kilometers. So can you guess, in a week you will be trying to go home with your GPS? Good luck. So general relativity is with us in everyday's life. However, again, if you go at the very large scales of the universe, very large scales, it could be that general relativity of Einstein is not the ultimate theory. It could be that the theory need to be extended to other theories. Actually, with a student of mine, Jacob Goldenhauer, we looked at more general theories. It's not theories that we proposed. I don't propose models. I test them. So these are the equations for general relativity, but they can be extended and modified. So we looked at a model like this and we tested it. So it could be that there are models of gravity that are more general than general relativity. And those ones, they will make the universe accelerate without a cosmological constant. It's called modified gravity. And there are, I wrote recently a review about them. So there is bi-gravity theories, non-local gravity theories, Horava-Lifshitz theory. There is maybe a half a dozen of theories that are well motivated and could explain cosmic acceleration without a cosmological constant. None of them are perfect. They all have some problems. So now we just covered the third. We did check this model. We find that it fits supernova very well, but it has some problems. So now, summarize with me. We have three possible explanations to cosmic acceleration. One is dark energy. Or you ask, what is a candidate? A candidate is vacuum energy. 2, a constant of nature. Just a constant of nature. And you can also call it a constant of nature in the laws of gravity. That's 2. And then 3, it could be that general relativity has an extension at cosmological scales. It's called modified gravity. In fact, these two, modified gravity, it's called modified gravity, and dark energy are the two most popular causes of possible causes of cosmic acceleration. And DOE, NASA, NSF, they are looking into a very important question. Is there a test that we can do so we can distinguish between one cause or the other? Okay? It's a very important. When someone tells you it could be A or B, the first thing that comes to mind, if you are designing an experiment, is to test how can you distinguish between A and B. Well, this I have to tell you about this one. So, two things that cosmology has given us today, and this is something is good to remember. So one is that we have about seven or even more probes of cosmology, data sets, different techniques to probe the universe, okay? It's a fantastic thing because in the 70s or in the 80s or even early 90s, people, they had one or two probes, you know, and they were not even sure about them. Nowadays, we have about 7 probes. They all work very well. Choose and work with the ones you like. The second thing that I want to tell you about cosmology, and I know that there are cosmology students here in the class, so cosmology gave us really a wonderful break. What is it? The break it gives us is that we have two classes of probes. One is to measure the expansion history. So the expansion of the universe has some probes related to it. That is one. The second one is actually, for 13.7 billion years, the way that structures have been forming in the universe. It's called the structure formation history. The structure formation history also has probes, has experiments. And then guess what? Not only you can use one and two, the other ones, you can use them to probe cosmology, but you can also cross-check them whether there is consistency or not, because they are based on different approaches. And that's the basis to test whether modified gravity of dark energy are the cause for cosmic acceleration. I thought this is an important point to mention to you. Well, and again, from observations. With my students, we developed, with Jason, Jacob, we developed a software that is online. You can Google ISIT-GR. It took us a little bit time, iteration to come with this name. ISIT general relativity. It's to test. Yes.
No.
I know that some colleagues, they didn't, in the UK, they call it actually ISIT tiger. I don't know why they made that connection. So the second thing I want to say is that if you are interested in this, for example, for the students, and you want something that has some pedagogical approach to it, I wrote a review last year. It's 200 pages. It almost killed me. It took a year to write it down. And it explains a lot these approaches for modified gravity, dark energy, and things like that. So who knows about, this is one more thing I want to say. Who knows about AstroPH? AstroPH. Google it. Google it later today. AstroPH is a server on the internet where every day hundreds and hundreds of astrophysicists, they put their papers, they put their research on the AstroPH. So you can daily see what is coming up in research. AstroPH, okay? It's for astrophysics phenomenology. It's an abbreviation. So now we get into the last cause of cosmic acceleration. So we did this once. We did a dark energy component, a GR cosmological constant or constant of nature, a modification to general relativity at cosmological scales, and then apparent acceleration due to the fact that we live in a relativistic cosmological model more complex than FLRW model. I was a big fan of this 15 years ago because I did general relativity for my graduate studies. And actually, I said that before we go and try to modify general relativity, let's see whether we understand very well the theory, right? And then, in fact, I want to ask you a question. So the Einstein field equations, the Einstein differential equations of general relativity, we talked about one solution, one exact solution. It's called the Friedmann, Lermet, Robertson-Walker model. And there's another popular one. Anyone? For black holes. It's another solution. Maybe Schwarzschild solution. So Karl Schwarzschild solution. So there's the Schwarzschild solution. So two solutions. But actually those are the most popular. But guess actually how many exact solutions there exist for Einstein field equations? About actually 1,200 exact solutions. To Einstein, there is a huge book like an encyclopedia to the exact solutions of Einstein field equations. Why? Because for the last 100 years, it was people were very proud when they derived an exact solution to Einstein field equations. It's kind of a recognition. So people derived so many exact solutions. But now what I want to tell you is that for cosmology, there are about 200 exact solutions to Einstein field equations. I do meet my colleagues at conferences and they did not hear about them. You have to be a Jedi of general relativity to hear about these solutions. So we looked into some of the solutions. I make always this analogy with the GIs and GR because Einstein and the people who brought up GR proposed so many possible things, and then we had the dark energy problem. So people want to run away from general relativity, but actually maybe general relativity still have answers to us. And I looked into it with some students, and there are some models that are called cosmological models, inhomogeneous cosmological models. This is always a question, guys, that we should ask ourselves, and girls, that we should ask ourselves. When you have a model, some of us here as faculty, we work with models in our science. The first question when the data don't fit the model or there is a problem, we should allow ourselves to say, maybe the model I'm using is not right. But in cosmology, people really think that the Friedman or Bergson-Walker model is the end of it. So, but actually, there are other models. I want to explain to you the idea of apparent acceleration. If we live in a bubble in the universe, if we live in a region in the universe that is underdense, not as dense as the rest of the universe, it is expanding. But because it's underdense, it's expanding a little bit faster than the rest of the universe. Make sense? Because we said matter slows down the expansion. So if we live in a light area in the universe, not as dense as the rest, it will expand a little bit farther. And if we happen to live in such an underdense region, we look around us, we have an impression of an apparent acceleration. It was a very popular idea 15 years ago. I was one of the fans of this idea, and we tried it. But it came at a cost. So when we looked, we worked on it with my students for 3 years, and then we realized why people did not work too much on it, okay? It was very involved mathematically and very difficult to work on it. But thanks to numerical integrations, we combine numerical integrations and analytical work. Well, this is the case I told you I would tell you about. So I was very enthusiastic. I wanted to prove that maybe the acceleration is an apparent one, okay? So I worked with my students, and after 4 years, we found out actually that it's quite the opposite. We found that if cosmic acceleration, the inhomogeneous model, they can explain very well observation of supernovae. But they cannot explain this. They cannot explain structure formation. See, I told you there are two things that need to be done: expansion and structure formation. So the Zakaras model that explains well acceleration does not explain structure formation. Here where is the data. So the data, this is where it should be and where the data is. Okay? And the Zakaras model is right here, the green model. So with my students, we got a physics review letter out of it. That's very nice. But we proved exactly the opposite of what we wanted. But it's fine. That's how it's science. Well, now let's recap. So what can cause cosmic acceleration? 1, dark energy. 2, a constant of nature. 3, modification to gravity. And 4, a possible apparent acceleration, not anymore. This is out. So this one is crossed out. So the 4th solution now really is that it could be something we don't suspect at all. Okay? So now I will give you my conclusions here. So we learned a lot about our universe in cosmology. There is a great concordance between probes. This is actually quite remarkable because if I have 7 probes, okay, I have 7 cosmological data sets, different data sets. And all of them tell me exactly the same story, that the universe has 23% of dark matter, 4% of baryonic matter, and about 70% of dark energy. All of them, they say the same story. All of them, they give me the same information. That is called cosmological concordance. So it's a concordance model. And so what I say, there is a lot of efforts to go after that W. You see W? W is the equation of state. Why is it so? Because if W is exactly -1, that means it's a cosmological constant. If W departs slightly from the -1, then it has to be something else. It's important. Well, I think to conclude, I tell you that 2 methods, two possibilities, we will hear a lot about them. This is 1 and 3 here. These 2, you will hear about them. Actually, I'm part of LSST, the Large Synoptic Sky Telescope, DZ, WFIRST, or Euclid. All the future experiments are going after these two probes, 2 possibilities. And I want to tell you something. There's a lot of data that is coming in cosmology. It's like what it used to be 100 years ago. The ideas are there. The problems are well clear. We have a problem of dark matter, a problem of dark energy. We have the data, and it's a great time to be a student in cosmology nowadays. Thank you for your attention.
Any questions for our speaker?
Yes.
Yes?
For the Casimir experiment,
Yes.
I know you had to simplify it for time's sake, but what led to the realization that there's a additional force in the vacuum between the plates that causes them to touch together, as opposed to gravity? Just know that gravity exists in a vacuum.
It is the I see your question. I think that's the masses of the plates.
So the plates did not actually touch, or
No, they don't touch.
Okay.
And the gravitational force between them is negligible.
Okay.
So it's certainly not the gravitational force that does that.
All right.
Yeah. Yes?
So do these, or do any of them, these explanations maintain the conservation of energy?
Yes, absolutely. Each single of them. Even that's a good question. I repeat the question. The question is, are all these possibilities? Do all these possibilities conserve energy? I agree with you. Conservation of energy is very important. The answer is yes. You hear a lot. Sometimes you hear a lot whether dark energy conserves energy or not. It does. What is important in general relativity is something more general than conservation of energy. It calls the continuity equation. This is the covariant derivative of the energy momentum tensor. What it means, in other words, let's put it into simple words. Conservation of energy, you need to combine it with the expansion of the universe. If you do that, it gives you what is called the continuity equations. So the answer is yes. I just gave you a little bit more information.
And
Yes.
yeah, so I've been thinking about dark energy for quite a while. I think it's sort of like a collective phenomenon when you have these molecules, like 4 molecules in this sense. These pairs attract, and then it kind of gives a repulsion effect in the center. It's kind of like similar to dark energy, where it's repulsive, like these voids in the universe.
Yeah, it is. In fact, voice will repel. So yeah, but the problem is we don't know of such molecules yet. That's the question. We don't know of such particles yet.
I mean, it could be the gases that lose energy due to gravity.
I hate to cut in on this, but our speaker doesn't have much time. We'll have to go back to UT Dallas this evening, but we do have time for dinner, and I'd love for as many of you as possible to join us for dinner. We're going to be meeting over at the Joyce Room here, and so if you want to come to dinner, now's the time, and yeah, we'd love to have you. So let's thank our speaker one more time.
I do have questions about